we can now compare our measurement to very precise theoretical predictions. So, Professor Witten, it's a pleasure to have you here.
On behalf of our rector, Professor Matteo Lodito, and the head of physics department, Professor Gennaro Miele, I'm very happy to welcome Professor Witten to Naples on this occasion. Professor Witten has shaped the whole body of research on theoretical high-energy physics over more than 40 years, and we are honored and happy that he could join our community on this occasion for 3 days and give his Majorana Lectures. So, with all our heart, thanks very much, and let the series of lectures get started.
So first of all, thanks very much for the kind introductions. And it's a pleasure to be here at the University of Naples. And as you can see from my title, I'm going to be talking about black hole thermodynamics then and now. That means that I'll start by describing the ideas from the classical period. And then in the second half of the lecture and also in the later lectures, I'll turn to a more modern perspective. So broadly, the 2 parts of today's lecture correspond to 2 views about entropy. Entropy could mean thermodynamic entropy, and then it obeys the second law of thermodynamics. Alternatively, one can take a microscopic point of view about entropy, and then you would say, we could start with classical physics, where of course the subject did start historically, but for brevity we'll start with quantum mechanics. In the quantum case, a quantum mechanical system in general, possibly in a mixed state, has a density matrix rho, and then one defines its von Neumann entropy, minus trace rho log rho. Now, under unitary quantum mechanical evolution, the density matrix is conjugated by a unitary operator, so the von Neumann entropy doesn't change. So the thermodynamic entropy obeys the second law, it increases, but the von Neumann entropy is constant, at least for an isolated system. The relation between the two is that the thermal entropy is the largest that the von Neumann entropy can be given the macroscopic state of a system. For example, if you specify observables that you can see macroscopically, like the energy, charge, and maybe density of a system and so on, the largest von Neumann entropy it can have given the macroscopic state is the thermodynamic entropy. But the actual von Neumann entropy might be much less. If you look at a system that appears thermal, it's very hard to know if it's truly in a thermal state in which the von Neumann entropy equals the thermal entropy, or if it's actually in or almost in a typical microstate drawn from a thermal ensemble, in which case the von Neumann entropy is very small compared to the thermal entropy. And later on, I'll go back in more detail to explain exactly this inequality. Oh, sorry. Apparently, I've moved it to this part of the talk. So to explain in more detail the statement that the von Neumann entropy is always less than the thermal entropy, consider a quantum system with n states that have observed values of the macroscopic observables. So I'm going to work in a microcanonical ensemble where rather than temperature and chemical potential, you specify the energy and the number of particles. And suppose you, after specifying the observed values of the macroscopic observables, you have n states. Well, a general density matrix of such a system can be diagonalized with eigenvalues that add up to 1, because the trace of rho should be 1. And one can interpret this to mean that the system is in the ith state with probability pi. Then the von Neumann entropy of such a state, the trace of minus rho log rho, works out like this. And with a little well, first of all, for a pure state where one of the p's is 1 and the others are 0, S is 0, because either p or log p is 0 for all I. For any p between 0 and 1, the contribution is strictly positive. So a pure state is the only case in which the entropy is 0. If you want to ask what its maximum is, a simple exercise with Lagrange multipliers shows that to maximize this quantity under the constraint that the sum of the p's is 1, the p's should all be equal. In other words, all states consistent with the macroscopic observations should be equally probable in order to maximize the entropy. But the state in which all states of the system compatible with macroscopic observables are equally likely is the microcanonical version of an equilibrium state with the given macroscopic observables. So the thermal entropy maximizes the von Neumann entropy given the macroscopic observables. So the von Neumann entropy of the equilibrium state, which is log n, is the thermodynamic entropy of a system that has n states accessible to it. So usually we just say that the thermodynamic entropy is the logarithm of the number of states, that's your n. And that's what the von Neumann entropy equals if the probabilities are all equal. Otherwise, the von Neumann entropy is less. Now, coarse graining and forgetting all microscopic details of a system that are not captured by macroscopic observables replaces the actual density matrix by one in which you have no knowledge of the detailed microstate, and you say the microstates are all equally likely. That's a thermal density matrix, and reduces to the case that the von Neumann entropy equals the thermal entropy. However, black hole thermodynamics began with thermodynamic entropy, so we will begin there. So at the very beginning was Jacob Bekenstein, who, inspired by questions from his advisor John Wheeler, asked what the second law means in the presence of a black hole. The second law says that for an ordinary system, the entropy can only increase. However, if we toss a cup of tea into a black hole, the entropy seems to disappear. To avoid this conclusion, Bekenstein wanted to generalize the concept of entropy so that the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, what property of a black hole can only increase? It's not true that the mass can only increase. For example, a rotating black hole can lose mass as its rotation slows down. And that's believed to be important astrophysically as an energy source for quasars. But there is a quantity that always increases. By coincidence, just as Bekenstein was asking this question, Stephen Hawking had just proved the area theorem, which says that the area of the horizon of a black hole can only increase in classical general relativity. So it was fairly natural for Bekenstein to propose that the entropy of a black hole should be a multiple of the horizon area. For example, here I've written the metric of a short-chilled black hole of mass m, a spherically symmetric black hole of mass m. The horizon is at r equals 2 gm, and the horizon area is 4 pi r squared, which works out to 16 pi g squared m squared. Since entropy is dimensionless, to relate the entropy of a black hole to its area, one requires a constant of proportionality with dimensions of area. From the fundamental constants h bar c and Newton's constant g, you can make the Planck length and the Planck area Lp squared. So Bekenstein's formula for the entropy was that the entropy is the area in Planck units. Or if I set the speed of light to 1, his formula was that the area is a over 4g h bar, except Bekenstein didn't know the constant 1/4. The constant 1/4 was provided by Hawking a few years later in a way that I'll explain. Now, so for a Schwarzschild black hole, the entropy is this one, given the area that we computed on the last page. Now, I usually set h bar to 1, but I've included it here because h bar in the denominator helps explain why black hole entropy is so big. The entropy of the actual sun is something like 10 to the minus 20 times the entropy of a black hole with the mass of the sun. So in other words, the sun as a black hole would have vastly more entropy than the actual sun has. So black hole entropy is extremely large compared to entropy of any ordinary system that we encounter. Now, Bekenstein's idea was that the entropy of a black hole was supposed to capture the information lost when the black hole was formed. He interpreted it as the logarithm of the number of possible ways to form the black hole. Somewhat vaguely stated. If you look at Bekenstein's paper, he doesn't make much attempt to explain exactly what that's supposed to mean. But loosely, this huge entropy was supposed to represent information lost when the black hole was formed. Bekenstein proposed a generalized second law saying that the generalized entropy, the area over 4gh bar plus the entropy outside the black hole, was supposed to obey the second law. In other words, according to Bekenstein, the quantity that always increases is not ordinary entropy, but it's black hole area plus ordinary entropy. So S out here was the ordinary entropy of matter and radiation outside the black hole. So the claim is that when something falls into the black hole, S out may go down, but A over 4gh bar increases by more. Now, when I look at the paper, I find that, as I've written here, since the generalized entropy increases when a cup of tea falls into a black hole, clearly generalized entropy defined this way is a thermodynamic entropy, not a microscopic von Neumann entropy. Bekenstein was a little bit vague about exactly what he meant by S out. But in the spirit of his paper, I think S out was the thermodynamic entropy of radiation and matter outside the black hole. He certainly didn't try to discuss a microscopic definition of entropy. Now, Bekenstein made a few tests of the generalized second law, which said that the generalized entropy should always go up. Here's one, perhaps the most significant one. Shine photons with wavelength lambda, and therefore energy 1 over lambda, on the black hole. The entropy of a single photon is of order 1, for example, because it has 2 polarization states. When the black hole absorbs 1 photon, its mass shifts by 1 over lambda. So if I assume that 1 over lambda is much less than the black hole mass, and I ignore a quadratic term in 1 over lambda, the shift in the black hole entropy, well, it's given by this expression, but I take only the linear term in 1 over lambda, and I get this formula for the change in the black hole entropy. Now, Bekenstein wanted the change in the black hole entropy to be bigger than the entropy that was lost when a photon falls into the black hole, which is of order 1. He observed that if the black hole is capturing a photon of size smaller than the Schwarzschild diameter of the black hole, say lambda, the wavelength is much less than 4 gm, then from this formula, the change in the entropy of the black hole is much bigger than 2 pi, which was satisfactory. But from the same discussion, you can see that, suppose that lambda is much bigger than the size of the black hole. If lambda is much bigger than the size of the black hole, then the change in entropy of the black hole is less than 1, which is unsatisfactory. Now, a black hole can absorb photons of any wavelength. Photons of very long wavelength are not absorbed very efficiently, but they are absorbed by a black hole. And Bekenstein really did not have a satisfactory treatment of this question. And as became clear a few years later, the question does not have a satisfactory answer in the framework Bekenstein assumed, which was that whatever falls behind the black hole horizon stays there forever. In thermodynamic terms, since Bekenstein assumed that the black hole does not radiate, one would have to assign it a temperature of 0. Thermodynamics says that at equilibrium, the change in energy E and entropy S of a system obey this well-known relation dE equals TdS, or ds equals dE over T. So if T is 0, then ds is infinity if dE is not 0. But Bekenstein wanted the black hole to have a finite entropy, not an infinite entropy. So his assumptions didn't completely fit together, And that was manifested in the problem he had in imagining the black hole absorbing a photon with a wavelength much bigger than the size of the black hole. In hindsight, you can't analyze the absorption of very long wavelength photons by the black hole while ignoring the fact that, as Hawking discovered a few years later, the black hole is strongly emitting such photons. Famously, Stephen Hawking discovered in 1974 that quantum mechanically, a black hole is not really black. It has a temperature proportional to Planck's constant. As preparation for explaining what Hawking did, I want to recall the idea of a Penrose diagram as a convenient way to depict and visualize spacetime. I know lots of you, perhaps the majority, are quite familiar with Penrose diagrams, but I don't want to assume that everyone is. So I'm going to give a brief explanation of what's a Penrose diagram. So first, in drawing a Penrose diagram, it's usually assumed that the geometry of interest is spherically symmetric. And then the azimuthal angles are suppressed. So only two variables are drawn: the time, which is plotted vertically, and a spatial coordinate, which you can think of as the radius, is plotted horizontally. And then a very important insight of Penrose was that it's convenient to make a conformal mapping that preserves causal properties in a way that I'll describe, but projects everything to a finite distance so you can draw the picture. So this triangle here is a Penrose diagram of Minkowski space. So the left vertical line is r equals 0. So what's plotted from left to right is the radius, or a function of the radius, because of Penrose's conformal mapping. The radius is 0 on this vertical line. This is the center of spherical polar coordinates. The radius is infinity, at this point labeled spatial infinity, but it's also infinite up here. As you go out, the diagram is usually drawn so that ingoing and outgoing light rays are at a pi/4 angle from the vertical. In fact, I've drawn that on the next page. So here, this purple line is meant to be at a pi/4 angle from the vertical, and that's the trajectory of an outgoing light ray traveling at the speed of light. An ingoing light ray would similarly be on a pi/4 angle from the vertical, but going in. So the time and the radius both go to infinity up here. But the retarded time is constant along the outgoing light ray, and the advanced time with the constant along an ingoing one. So you could think of this line up here as being, it's actually called future null infinity. It's parameterized by the retarded time. So an experimentalist who's at a big distance looking at what is coming out, massless particles coming out of space-time, you could think of as making measurements somewhere up here. And those measurements are parameterized. Well, of course, the experimentalist probably has a watch and measures the time, but to infer where the signal came from, you really measure the retarded time. Now, the Penrose diagram of a black hole is somewhat similar. Okay, sorry. Let's go back here. A massive observer like us, traveling at less than the speed of light, is at an angle to the vertical that's less than pi/4. And a massive particle will end up at this point, which is future infinity. So if our experimentalist is massive, the experimentalist is really making measurements pretty close up here, but still capturing signals from large retarded time, coming out late, perhaps, from the spacetime. Now, in Minkowski space, from future infinity, you can see everything. Everything, the whole triangle is in your past. Remember, a causal signal, a signal that's traveling at or below the speed of light, is at an angle less than pi/4 from the vertical. And each point in the triangle connects to future infinity by a line that's at an angle from the vertical less than pi/4. Now, the black hole is similar, except that, first of all, future infinity is this point up here. And looking to the past from future infinity, you can't see the whole space-time. So this black line, it's meant to be at a pi/4 angle from the vertical. I'm afraid it's not carefully enough drawn. But this black line labeled the horizon is the boundary of what you can see from anywhere up in the future. You can, looking to the past, receive signals that travel no faster than the speed of light. you can receive signals from this portion of the space-time. But the horizon is the surface of no return. Anything beyond the horizon will end its life at the singularity, which traditionally is depicted by that wiggly line at the top, and will not escape to the outside world. Infinity in the outside world is this black line. This picture also has, I've sketched the star, which created the black hole. So, well, in this conformally drawn picture, the star originated at this corner of the diagram in the past. But you have to remember, the star probably always had a positive size, maybe even collapsed from a huge cloud of dust. It's Penrose's conformal mapping that maps the past of the star to this point, regardless of how the star really originated. Then the world history of the star fills out this red region, and it ends its life at the singularity. So anyway, that's the geometry in which Penrose analyzed quantum fields in order to eventually prove that Bekenstein had been correct. Now, physics as we understand it is causal. Whatever we observe now could be traced back to what existed before on some initial value surface. And it could be any initial value surface to the past of the observation. So whatever the observer at future null infinity, in other words, whatever the late time observer far from the black hole will measure, can be traced back to initial conditions on the quantum field on an earlier hypersurface. This is true no matter where you put the earlier hypersurface, but for Hawking's discussion, a convenient choice is to take a Cauchy hypersurface. Cauchy hypersurface is just a fancy name for initial value hypersurface. A convenient choice is to pick a hypersurface that crosses the horizon to the future of the collapsing star. So the red region was the world volume of the star. My Cauchy hypersurface that I've drawn in blue starts at r equals 0. It ends at r equals infinity, at spatial infinity. It's a complete Cauchy hypersurface. Any signal anywhere to the future, for example, traveling no faster than light, had to originate from somewhere on the surface. But I've picked it so that it crosses the horizon in the white region outside of the star, and if you like, to the future of the star. So, to the future of where the star crossed the horizon. So the region, okay, the blue hypersurface eventually passes through the star, but the portion of it that's outside the horizon we can assume is essentially in vacuum. The star has collapsed, and maybe there were some transients that it created, but after a while it died down, and there was more or less nothingness outside the horizon. Now remember, signals in this picture travel at a pi/4 angle from the vertical. So here these diagonal lines are meant to be at a pi/4 angle from the vertical, and they're signals that travel from the blue hypersurface to the observer at infinity at the speed of light. That's a schematic representation of such signals. Now, what is the observer going to see? Part of Hawking's insight was that although the full details of exactly what the observer will see depends on the details of the collapsing star, if we ask what the observer will see in the far future after transients die down, we will get a universal answer. The most important point about this picture is that a signal that's received very late originated from very close to the horizon. So very late means very, very far up on this black line, up to future infinity is really the corner of the picture up here. For a signal from outside the horizon to get up there, it has to travel very close to the speed of light, originating very close to the horizon. We'll make that more quantitative in a moment. Now, remember that the relevant region outside the horizon is outside of the star, so it's essentially in the vacuum state. So observations made at late times depend on measurements of the state of the quantum field at short distances. Short distances here meaning very close to the horizon. But every state is equivalent to the vacuum at short distances. So when the observer collects photons coming out of the black hole a long time after the black hole formed, delay time observations of the observer probe the vacuum state near the horizon at short distances. So for example, the LHC probes the vacuum down to a distance of roughly 10 to the minus 17 centimeters. But as I'll explain in a moment, by making late time measurements outside a black hole, you can, in theory, if you were really able to do that experiment, if you really had a black hole at hand, and you could measure what was coming out of it, you could probe the vacuum down to much smaller distances. It's because the vacuum state is universal at short distances that Hawking got a universal answer for the late time behavior, regardless of exactly how the black hole formed. So to explain this in more detail, well, I'm going to redraw this picture, the same picture as this one, but I'm going to draw a version of it where we only focus on the part that's important, which is this little bit. So it's the same picture as before. The diagonal black line, which is supposed to be at a pi/4 angle from the vertical, is the horizon. This line, also at a pi/4 angle from the vertical, is the far future, where you can think of the experiments as being made. And the far future is parameterized by t, really by retarded time. We want to parameterize it. And then I've drawn a little bit of a Cauchy hypersurface in red. I don't care what the rest of the Cauchy hypersurface is. The late time signals coming from near the black hole came from this little bit. So I've emphasized that. So let u be a coordinate function that vanishes on the horizon on some Cauchy slice. The precise definition of u won't matter. Let t be the retarded time of the signal detected by the observer at infinity. The relationship between u and t is this one. So you see, if u were negative, you'd be behind the horizon, and the signal would never emerge. At u equals 0, the signal only emerges at time infinity. If you start at a very small positive u, the signal will eventually emerge, but only at very late times. Because it takes, if you're a tiny distance outside the black hole horizon, you can escape, but you will only escape at very late times, as seen by an outside observer. And if you make that quantitative, by solving the geodesic equation for an outgoing null geodesic, you find that the short till time, or equivalently the retarded time at which the signal escapes, is 4gm times the log of 1 over u, plus a constant, c0. So you can find that formula by solving the geodesic equation, but if you're familiar with the Kruskal-Sakaras coordinates for a black hole, you don't even need to look at the geodesic equation. In the Kruskal-Sakaras coordinates, the equation for the outgoing geodesic is just u equals constant. And this equation is just the relationship between Schwarzschild time and the Kruskal-Sakaras coordinates. Or more exactly, that relationship reduces to this near u equals 0. So if you reparameterize u by rescaling it, you would shift the constant c0, which won't be important. And nonlinear redefinitions of u are even less important. So exactly how you measure the distance from the horizon isn't going to be important. No matter how you measure it, the time grows logarithmically as u goes to 0, and that's all that's important. Yes?
I'm asking a stupid question.
Yes, please.
I'm not familiar.
Yes?
So what I answer is, what is t? Because you write t is the time at which the signal is detected at infinity. But isn't this should be infinity as well?
Well, what's called retarded time is the difference between time and distance. So if your distance r from the black hole and your watch reads t, then t minus r is called the retarded time. In Newtonian physics, that would be the time at which the signal was emitted. In relativistic physics, that's not precisely correct. It's roughly correct. So the t that enters this formula is really, you see, retarded time is the natural parameter that an experimentalist would use. We're a billion light years away from the black hole that created the signal that the LIGO detector saw. So the time on our watch has nothing to do with when it was emitted. We subtract 1 billion years because we're 1 billion light years away. So, however, an additive constant in the time isn't very important for what I'm saying. So, assuming you stay at a fixed r when you're making your observations, which is most likely what an experimentalist would do, it doesn't really matter whether you parameterize them by t or by t minus r. That's why I'm being a little bit casual about exactly what I mean by t. Anything that measures the time in the sense that every second it increases by 1 second will do. Any other questions? Well, so as I said, the time at which the signal escapes increases logarithmically as the origination point of the signal goes to 0. But we can solve that for u in terms of t, and it becomes dramatic. We find that u is exponentially small. So for example, for a black hole with the mass of the sun, 4 GM is something like a few milliseconds. So if t is 1 second, then the exponent here is a couple of hundred. And u is e to the minus 200 in some units, which it doesn't matter very much what they are because e to the minus 200 is so little. And so you see that if you wait till 1 second after a solar mass black hole forms, your observations will probe the vacuum at distances vastly less than the LHC or any other experimental device can reach. So you're probing the vacuum at short distances, and that's why you get a universal answer. So as I've just said, if t is large, u is exponentially small. du dt is also exponentially small. So a mode observed at infinity will have undergone an exponentially large redshift on its way. So what you detect at any given energy at a sufficiently late time originated from a very high energy mode near the horizon. That's why there's a simple answer. A mode of very high energy propagates freely along the geodesics I've been drawing. So now, what does the observer measure at infinity? The observer at infinity measures a quantum field. It might be the electromagnetic field. Most realistically, you'd measure the electromagnetic field. You would detect photons. To shorten the discussion, I'll imagine detecting a general quantum field, psi of t. And what do we observe? A typical observable is a two-point function of the quantum field. For example, the square of the electric field is the intensity of the radiation. So a device that detects photons would be measuring a two-point function of the electromagnetic field. But since I don't want to get into all the details of Maxwell's equations, we just imagine we're measuring the two-point function of some quantum field. Now, near the horizon, if the field psi, okay, quantum fields at short distances have power law singularities typically. To write a specific formula that happens to be particularly simple, if psi is, for example, a free fermion of dimension 1/2 in the 1 + 1 dimensional sense, then the two-point function near the at short distances would have a simple 1 over u minus a simple pole, a 1 over u minus u prime singularity. Now, to go from what would have happened near the horizon to what the observer measures at infinity, we just change variables from u to t by this formula. And then we find that this formula transforms into this one, literally simply by changing variables by this equation. Now, you can see that this expression is anti-periodic in imaginary time. It's odd under shifting the time by 8 pi gm times the square root of -1. For fermions, anti-periodicity corresponds to, well, in quantum mechanics, thermal correlation functions are periodic or anti-periodic in imaginary time for bosons or fermions. So here I did a fermion and I got anti-periodicity. For a boson, we would have had u minus u prime squared, and we would have gotten periodicity. But regardless, we get periodicity or anti-periodicity in imaginary time with period 8 pi gm. And in quantum mechanics, that's a signal for a thermal correlation function at a temperature which is the inverse of the period. So we've discovered that what the observer would measure at infinity is a thermal correlator at a temperature 1 over 8 pi gm, which is called the Hawking temperature. In other words, a black hole, after transients that depend on how it was created die down, radiates thermally at a temperature 1 over 8 pi gm. The observer at infinity will measure the same correlations as if you were in a thermal ensemble at that temperature, because in fact, the outgoing modes are in a thermal ensemble at that temperature. That explains why Bekenstein had trouble making sense of the interaction of the black hole with low energy photons. You see, the photons that are bigger than the size of the black hole have an energy less than the Hawking temperature. And that means that at the Hawking temperature, each mode of such a photon is multiply occupied. The black hole is strongly emitting at that frequency with many photons in each state. And to analyze the absorption of one photon while ignoring the fact that many photons of the same kind are being emitted at the same time, it gives the wrong answer. That's why he had trouble making sense of the interaction of the black hole with very low energy photons. We can also now confirm Bekenstein's formula for the entropy. Using dE equals TdS, we take E to be the black hole mass, and we take the Hawking temperature for T. T is 1 over 8 pi gm. So we learned that ds is 8 pi gm dm. So S is 4 pi gm squared. So this formula was for a Schwarzschild black hole. So when this formula was computed for Schwarzschild, or this one that it came from. So here, the temperature was for a Schwarzschild black hole. And so E equals m, and this T we should use for Schwarzschild black hole. So we get this, which integrates to S equals 4 pi gm squared. But earlier we computed that the area of a Schwarzschild black hole is 16 pi g squared m squared. So the entropy is A over 4g, which agrees qualitatively with Bekenstein and shows that the constant that was unclear in Bekenstein's work is 1/4. Maybe I'll stop and ask if there are questions on this derivation.
Massimo. Right bottom.
So the two-point function that you showed goes to 0 also if you separate the 2 points. So it's exponentially suppressed because it has an exponential in the denominator. If you send t, one of the two t to...
Well, the way it's suppressed is just that the radiation from the black hole spreads in space. So if you're at a big distance, the intensity of the radiation falls off as 1 over r squared.
Yes, but if it is exponentially suppressed, then can you trust
it
this
wasn't
perturbation?
exponentially suppressed. There's something
in the
wrong with that
denominator.
statement.
If t goes
It's not
to
exponentially suppressed because t and t prime are comparable. You see,
okay, but if you send t to infinity?
T and t prime are both large, but t minus t prime is fixed. The experimentalist makes a measurement at late times, but at fixed frequency. To make an observation at a given frequency, you take the Fourier transform of this in the variable t minus t prime. So keeping the frequency fixed means that you keep t minus t prime fixed. In other words, if what you're measuring are photons, you measure the correlator between the electric field at time t and the electric field at time t prime. The Fourier transform of that has to do with the intensity of photons at frequency omega. So this is not exponentially decreasing. Well, you should ask me why it doesn't decrease. As written this way, it looks like it doesn't even decrease like a power law. I think that's hidden. Okay. If we write this in physical units, it would eventually decay like a power. Well,
yeah.
I think, as written, I've assumed that the observer integrated over the celestial sphere at time t and collected everything that was emitted at a given time. So if we made a local measurement, we'd get a 1 over r squared. But since we've implicitly integrated over the celestial sphere, there's now 1 over r squared. So there's no suppression. This is invariant under shifting both t and t prime by a constant. Any other questions? Yes?
Wolfgang. Right bottom.
How important is it that you assume fields for the conformal behavior? You
It's
assume the
not,
dimensional
it's
number.
not important at all, but I could have used one of my other 2 lectures to do the calculation without assuming that. I wasn't planning to, but it would be one option. By assuming it was conformal, I had a simple answer here. And, okay. The physics of what I swept under the rug are what are called the gray body factors for black holes. So as I've presented it, there's no gray body factor. The gray body factor is extremely important in understanding the details of the physics of a black hole, but for understanding the basic idea of the Hawking effect, I think it's not important. So I think I've explained the basic idea correctly, but if we want to be more realistic, I should make a more realistic model of the quantum field we're observing, and then we would indeed find the gray body factors. What it means roughly, what gray body factor means roughly is that if we'd written an equation if we do Maxwell's equations, for example, in the field of a black hole, there's a centrifugal barrier between the horizon and infinity. And an outgoing photon might be reflected back by the centrifugal barrier. So the radiation is reduced by the probability for a photon to tunnel through the barrier, or perhaps over the barrier if its energy is big enough. So it's interesting that outgoing photons might be reflected back. But the basic idea of the Hawking effect is that outgoing photons are created in the first place, which I've explained. So I think what I've explained is what most people would want as a first orientation to the Hawking effect. Any other questions?
I was wondering whether... Again, something very rough just to see
Yes.
where I am with this. So, so you're saying one could be surprised that Hawking entropy is valid independently of the way in which the black hole is formed.
Yes.
And in a sense, you should expect that out of thermodynamics, because if it is a sort of equilibrium or a steady state, you should have that the final state is independent on the initial conditions. And so maybe what...
But it's surprising that the entropy is so large. Classically, there's a no-hair theorem, and the black hole has nothing except mass, charge, and angular momentum. But quantum mechanically, it has an entropy much bigger than any ordinary system.
I was also having another take on what you say. Let's say that you're showing with this type of arguments that the fact that the entropy is so large and is
Yes.
independent on the initial condition is a fundamental property of space-time and quantum fields.
Yes.
I don't know if this is... You see, my point is that what's the connection between the validity of thermodynamics and the fundamental property of space-time?
Well, you're raising the point that Hawking raised half a century ago. It does look like there's some kind of deep connection between space-time, quantum mechanics, and thermodynamics, but we haven't gotten to the bottom of it. I will tell you some more contemporary viewpoints as these lectures proceed, but we certainly haven't gotten to the bottom of it. Any other questions?
A question regarding the form of this conformal two-point function. I guess I asked for confirmation that those du prime is just a way to keep track of how it transforms under
Yes, the
coordinate
du
changes.
to the 1/2 was just to let me, yes, that's right.
Okay, and I was wondering, why are we assuming conformal behavior with respect to the u coordinate, for example, rather than the t coordinate?
Oh, because in the u coordinate we're in the vacuum.
Okay.
We're observing correlations in the vacuum at short distances. It's actually natural to. Well, quantum field theory tends to be approximately conformally invariant at short distances. But all that I really cared about here was that quantum field theory produces power law singularities at short distances.
Yes, I understand.
Okay.
Thank you.
Well, I wasn't planning to do this, but as I told a previous questioner, one of the other two lectures could be about a massive scalar field that isn't conformally invariant. And then we would see exactly how this derivation changes. The way it changes is that, as I told the previous questioner, we'll get what are called the gray body factors. We'll get thermal emission modulated by the probability for the mode to tunnel through a potential barrier outside the black hole. But here we've essentially assumed free propagation to infinity. Any other questions? Now, many observers, ever since the work of Hawking and Bekenstein, have thought that somehow the entropy A over 4G means the black hole can be described by some sort of degrees of freedom that live at its surface. 1 bit or qubit for every, I wrote 1 over 4G, but it should have been every 4G of area. For example, in a famous article in 1992, John Wheeler drew this picture where he envisaged the surface of a black hole being divided into little units of area with a bit living on each of them. And if you read the article, you'll see that his bits are supposed to rise from measurements of the spin of a spin-half particle, for example. The term qubit hadn't yet been coined when Wheeler was writing, so he couldn't have referred to qubits. But he does emphasize that everything is of quantum origin. Now, Hawking's approximations assume the radius r of the black hole is much bigger than the Planck length because he ignored fluctuations in the geometry, which would be important near the Planck length. And Hawking's approximations are good for as long as that's true. For example, a solar mass black hole with an initial mass of 10 to the 33 grams will shrink down to a mass of order 10 to the minus 5 grams before Hawking's approximations break down. We don't really know what happens at that point, but we presume that eventually the evaporation finishes and we're left with stable elementary particles. A fundamental point about Hawking radiation is that the radiation appears to be thermal even though the black hole could have formed from a pure state. Not only it could have formed from a pure state, but in the real world, black holes form from what's pretty close to a pure state. As I told you before, the thermodynamic entropy of the sun is roughly 10 to the minus 20 times the entropy of a black hole, the mass of the sun. And whatever the sun formed from could only have had a smaller entropy. So the sun formed from a very low entropy state compared to, a black hole in the real world formed from a very low energy state. And let me try again. A black hole in the real world forms from a very low entropy state compared to its entropy as a black hole. So in the real world, black holes originate as close to being pure states. Yet they appear to radiate in a purely thermal fashion. That's presented a puzzle that drives much of the research in this field, and that to this day is only partly resolved. The puzzle is, how can you get what appears to be purely thermal radiation from something that is born in almost a pure state? We'll make the puzzle more quantitative at the end of the talk, and also I'll explain a little bit of what is understood now. Hawking's approximations are valid for almost the whole evaporation process of a solar mass black hole and seem to show that the outgoing state is thermal ultimately with a very large entropy of order the mass over the temperature, or a huge number in the case of a solar mass black hole. But if the formation and evaporation of the black hole are described by ordinary laws of quantum mechanics, then if the initial state is pure or almost pure, the final state should be the same. Concretely, the reason that Hawking got his answer, where the radiation seems to be thermal, even if the black hole is in a pure state, is that observations of the distant observer amount to observing the quantum fields only outside the horizon. Even if a black hole formed from a pure state, so that we can assume that the state of the whole universe is pure, the quantum fields are restricted to only a portion of space-time or in a mixed state. So in the Hawking process, we're observing a signal that comes from a mixed state, so naturally it doesn't look like we're seeing emission from a pure state. I just want to go over a little bit how this works in ordinary quantum mechanics. Suppose you have a system with two parts A and B. They have respective Hilbert spaces HA and HB. In quantum mechanics, the Hilbert space of a combined system is the tensor product HA tensor HB. Suppose we start with a pure state psi AB in this tensor product Hilbert space. To a pure state, we can make the pure state density matrix, which is just the projection operator onto psi AB. The expectation value of any operator OAB in that state, well, it's given by this. But by moving the bra over to the right, we can write this as the trace in the AB Hilbert space of the operator OAB times this pure state projection operator. This is just a tautology that doesn't do much for us. Rho AB is the orthogonal projection operator on the state psi AB. So in particular, its Hermitian non-negative, its trace is 1, and also it has rank 1. Now suppose we're only going to observe the subsystem A. That means we consider only operators of the form OA tensored with the identity on system B. So now the expectation value of the operator in the state psi AB is still given by a trace. And the trace means a sum over all states of the AB system, which means a sum over all states of the A system and also a sum over all states of the B system. But because the operator on B is just the identity, the sum over the states of the B system is trivial, and we can do it more or less explicitly to get what I'll call rho A, which we get by summing rho AB over all states of the B system. And then we find that the expectation value of an operator that only acts on the A system in the state psi AB is the trace of OA times rho A, where rho A is called the reduced density matrix for system A. In other words, for measurements in system A only, we can use the density matrix rho A, which is obtained from rho AB, by taking a partial trace on HB. System A then has a von Neumann entropy, which I introduced at the beginning, minus the trace of rho A log rho A. And in this case, it's called entanglement entropy because it arose entirely from the entanglement of system A with another system B, with the overall state being pure. The idea to understand black hole entropy in these terms was apparently first put forward by Raphael Sorkin in 1983 in a paper that initially attracted only modest attention. Then it was developed further by Sorkin with Bombelli, Cole, and Lee, I think. The idea was the following. In a quantum field theory, divide space into two regions, A and B. In our application, B will be the region outside, behind the horizon, A is the region outside. But in the general discussion, there could be any A and B. Let psi be the vacuum state, and let rho A be the reduced density matrix of the vacuum for the state psi. You can try to calculate the entanglement entropy SA And that's what Sorkin did here in more detail in the second paper. You find it's ultraviolet divergence, but the coefficient of the divergence is proportional to the area A of the boundary between regions A and B. Sorkin's idea in modern language was that somehow gravity cuts off the ultraviolet divergence, replacing A times infinity, which is the answer without gravity, by the Bekenstein-Hawking answer, A over 4G. Another way to say it is that Sorkin ignored gravity, so that was like having G equals 0. And A times infinity is the correct answer when G is 0, according to Bekenstein and Hawking. So Sorkin's idea makes a lot of intuitive sense as it matches two ideas. One is that A over 4G is the irreducible entropy of the system for someone who has access only to the region outside the horizon. And the second is that the divergence in the entanglement entropy is proportional to the area because it comes from short wavelength modes near the horizon. As if, after cutting off the divergence, the density of quantum degrees of freedom on the horizon per unit area is 4G, as in Wheeler's picture. Again, 4G, not 1 over 4G. Susskind and Uglum made a simple observation that strongly supports the idea of interpreting S out as entanglement entropy. If we interpret, so remember, Bekenstein was vague in what he meant by S out, but I think most people reading the paper would assume that S out is the thermodynamic entropy outside the black hole. Instead, Sorkin said that S out should be interpreted as the von Neumann entropy of the quantum fields outside the black hole, which is the way its relation to the thermodynamic entropy is that the thermodynamic entropy is an upper bound, but it might be much less. If we interpret S out this way, the generalized entropy defined by Bekenstein is better defined than either term on the right-hand side is separately. The second term has the ultraviolet divergence that Sorkin noted. But Susskind and Uglum pointed out that there's really an ultraviolet divergence in the first term also. When Hawking wrote his famous paper on black hole evaporation, he didn't calculate loops that renormalized the Newton's constant. So presumably Newton's constant in Hawking's paper was the bare Newton's constant, G0. But when Bekenstein wrote about generalized entropy, which was supposed to be a formula that holds in the real world, presumably Bekenstein meant the observed physical Newton's constant by G. And so you have to consider the relation between G and G0. And that relation involves a renormalization, which at the one loop level looks like this, where C is a constant at one loop level. Susskind and Uglum argued that the ultraviolet divergences in S out cancel those in 1 over G and showed that that was true at the leading order. And later authors have improved this derivation, improved the derivation and confirmed the claim.
What is the origin of cancellation?
What's the origin?
Of cancellation. What's the reason for the symmetry?
Well, that's something I might explain in one of the other lectures. So I wasn't, well, let's keep that question. The question was, why does this cancellation happen? So, I'll maybe aim to explain that in one of the other lectures, but not today.
How long more before the end of this first part?
We could declare the first part over in a minute or two.
Very good.
This might be a good place to stop, let's see. Yeah, okay. This is the place to stop.
Okay, let's thank Edward. So, question?
I see a question in the back. There's one in the back.
Way in the back.
Yeah, shout.
when you have the quanta very close to the horizon off to infinity, well, it's true that they come from the very UV of the theory, but when you say that they fly off to infinity, it takes back reaction. Getting lighter in time affects the dynamics of this quantum.
Okay, the question was if we have to worry about the fact that while the photon is propagating from near the horizon to infinity, the black hole is getting lighter. Well, it depends. Suppose the evaporation of a solar mass black hole takes maybe 10 to the 50 years. So if we're 1 light year away making our observations, it will have evaporated by 1 part in 10 to the 50. So 1 light year is a huge distance from a solar mass black hole. That is effectively an observation at infinity. And the evaporation is so slow that it's negligible in that time scale. You are correct, though, of course. The evaporation does affect the geometry, and the photon propagates in the geometry that actually exists with its time dependence.
Thank you.
Just speak up.
So we said that basically what we observe as a late time observer are modes that had a really high energy at some point during their traveling.
Yes.
They redshifted to a finite energy.
Yes.
Infinitely or exponentially.
Right.
So I was wondering, isn't this an issue, like how do we reconcile this with the fact that we do not know the ultraviolet behavior of gravity? I mean, is this an issue in general of our mathematical theory?
Well, okay, that's an excellent question. So the question was, since we don't know physics at arbitrarily short distances, is that a problem for the calculation? Well, let's discuss exactly what the calculation needed. It was up to me to pick a Cauchy hypersurface which I wanted to pick. So I want to pick one where the signal arises at a frequency that's above the Hawking, much above the Hawking temperature, wavelength which is very short compared to the size of the black hole, but where I still know the laws of nature. So I don't have to put the blue hypersurface where the photon had an energy of 10 to the 100 GeV. I could, if it's a solar mass black hole, I could put the blue hypersurface where the photon had an energy of 2 eV. 2 eV is a huge energy compared to the size of a solar mass black hole. And we know the laws of nature at 2 eV. So it was enough. It's interesting that we can go to very, very short distances, but it's enough to know the laws of nature. In the case of a solar mass black hole, which is so big, 2 eV is a wavelength of 10 to the minus 5 centimeters or whatever, right? So that's 10 to the minus 11 times the size of our solar mass black hole. So 2 eV can here be regarded as a huge energy if we're observing a solar mass black hole. But it's an energy where we're comfortable with our understanding of the laws of nature.
Okay, so it has 2 eV while near the horizon before the redshift.
No, the energy was 2 eV here. The energy is 2 eV here. I'm the one who picks the blue hypersurface. So I picked it. Okay, first of all, a black hole with the mass of the sun is radiating at something like 10 to the minus 11 eV. So we're observers with very, very big telescopes or something, so that we can measure such long wavelengths. But my calculation tells me that the signal originated at much shorter distances. And to make sure I understand it, I'll draw this blue hypersurface so that the photon that I detect with 10 to the minus 11 eV had 2 eV when it was on the blue hypersurface. I've picked 2 eV because it has 2 conditions. It's low enough that I'm confident I know the laws of nature there, but it's high enough that it's way above the Hawking temperature and way above the inverse size of the black hole.
You said you cannot observe it because it's going to be redshifted and large there. So the distant observer is not going to understand anything because it is redshifted a lot. That if I take the energy that high, that low, then it seems to be.
Yes, yeah, that's correct. So at the LHC, we probed the vacuum down to 10 to the minus 17 centimeters, and we actually learn what's there. I think what you're saying is that that's not really true here. Here, we get this universal Hawking effect. And so what we actually learned about the vacuum is limited. Because, as I said, with the photons, it's sufficient to trace it back to an energy of 2 eV. And so it doesn't, there's some fine print I'm ignoring, but basically it doesn't depend much on what there was at higher energies.
More question?
When you solve the geodesic equation to extract U, this function, or you said that C0, which is the integration constant when you relate to the time, is not important.
Yes.
But when you extract U, it has essentially C1, which is which determines the value of this U. Or maybe I didn't understand well this point.
Well,
Because I think it is playing a role, this constant C0.
not really.
If I understand.
Let's try to find the formula.
Yeah.
Sorry, that must have gone too far. Well, the point is that if you change U, that would be equivalent. If you change C0, that would be equivalent to resetting your watch. If you changing C0 could be absorbed in shifting the time by a constant, and the observer at infinity has no natural zero of time anyway.
Okay, you only shifted the time, so it's shifting zero. Okay.
Yes, I was looking. Here's okay.
Yes.
Here's the formula.
Yes. Yes.
So if we change C1, that's equivalent to adding a constant to the time. So.
Okay. Okay. Just a matter of T0. Sorry.
Okay, I think let's thank again Edward, and we come back at 11:50. Okay.
I'm very thirsty. If there's a drink here, I want to.
Yeah, please.
sì, allora lo si parla? Vediamo se sentono. Ah, ecco qua.
Prova?
Vedete se sente. Prova. Ancora? Ancora? Perfetto. Perfetto, bravissimo. Prova. Ok. Sì. Ti ricordi di invitarsi a pranzo, a cena, ma parliamo al CERN nel 94? 94, sì. Vabbè, se è lui il nostro padre.
Sono anche molti da fuori.
Io non l'ho mai visto. Ma si vedeva che ancora tecniche domande io non so, però mi sembra che la gente sapeva quello che diceva. Sono stato 15 giorni a Camogli, a aprile. No, ho dovuto fare riabilitazione, ho fatto un'operazione, c'è un centro là molto è meglio sempre fare farma che non farma. Era giusto prima di quello che è successo. Ma che non ci fa, sappiamo che va che tutto finisce a Tarallucci qui, sembra tutto che non è nulla di serio.
Alla fine credo che c'è una sorta di solidarietà di umanità del sistema. È difficile che poi vadano, cioè riescano.
What? You made it to the Facebook? Yes. Okay. I wasn't sure. Having good lunch. So great to I've never seen this lecture before.
Gliel'ho detto che stavo molto scoperto, ma glielo diciamo più. Di cercare di parlare un po'. Non glielo diciamo, noi dobbiamo andare al massimo. Mi dispiace non aver fatto disturbare, però ho detto, guarda, lì, non è giro, no? Io ho finito il mio lavoro.
We just need to get it. This is one thing that we haven't
Yes, exactly.
Now I have the song in my head.
I posti per l'anno, ma nella protesta, nonostante c'era un ordine mestiere mi diceva che siccome allora se Laura Rocca finiva in degli scoperti non è molto soddisfatto perché guarda, diciamo, come se ricerca nella pratica è stato calcolato, non è una e quindi non allora lei c'ha sti contatti, se quelli per l'acquisito, se quelli per il giusto e per la certezza mettiamo un po' di mani, poi vorresti andare. Fammi vedere fuori a me,
Please take a seat.
Senti di queste cose qua. Così Marco si siede là. Marco è il teloforo dei microfoni. E siamo.
Okay, I think we can start. And there is a request, please, when you ask for a question, wait, please. Wait for Marco to bring you the microphone. Then if it doesn't work, shout. But okay, we start the second part and now. Before was then and now is now.
Can you hear me in the back? So, as I explained in the first part of the talk, the starting point of black hole thermodynamics was the mysterious claim that the purely geometric quantity A over 4G is an entropy. And I stress that this is a thermodynamic entropy that obeys a generalized second law. I also emphasize that the other side of entropy is the purely microscopic von Neumann entropy, minus the trace of rho log rho, where rho is the density matrix. In general, the relation between them is an inequality. The von Neumann entropy is no bigger than the thermal entropy. Well, is there a geometric or gravitational formula for the von Neumann entropy? In fact, there is such a formula. The first version was discovered by Ryu and Takiyanagi, and there were several later improvements. I'll try to motivate the original version of the formula. So remember, the simplest solution of Einstein's equations is the Schwarzschild solution that describes a black hole, a spherically symmetric black hole. It's a good solution when r is bigger than 2 gm, which is the position of the horizon. The horizon is at r equals 2 gm, where this factor vanishes. And the coordinate system breaks down. And the solution describes the gravitational field outside any spherically symmetric body, such as the sun, to high accuracy. However, if a spherically symmetric body undergoes gravitational collapse to r less than 2 gm, the solution is incomplete because it becomes singular at 2 gm. And various researchers discovered in the 50s and 60s that this is only a coordinate singularity. I'm sorry that you're not seeing the bottom. Well, sorry, this isn't helping. It's only a coordinate singularity. The solution can be continued to r less than 2 gm. The full maximally extended Schwarzschild solution is quite remarkable. It describes two asymptotically flat worlds connected by a wormhole. The wormhole is sometimes called an Einstein-Rosen bridge because Einstein and Rosen discovered part of the picture in the 1930s. Now, here's a cartoon version. I'm going to show a Penrose diagram. But for convenience, I've drawn the Penrose diagram for a world with a slightly negative cosmological constant, which makes it easier to make the point I'm going to want to make. So the maximally extended diagram has the property that it describes two asymptotically flat worlds. One is on the right, one is on the left. I imagine a right observer who lives here and a left observer who lives here. If the cosmological constant were 0, this triangle here would be more like a diamond with spatial infinity way out here. Instead, a small negative cosmological constant gives an infrared cutoff and makes the picture look like I've drawn, with a sort of vertical boundary, a time-like boundary, where the left and right observer could be living. So there are two asymptotically flat worlds. One is on the left, one is on the right. Geometrically, they're connected. But the connection is very much like quantum entanglement. Quantum entanglement is a correlation between two systems, but it can't be used to communicate information. If I have an electron that's entangled with your electron, knowing that entanglement doesn't enable me to manipulate my electron in a way that would send a signal to you faster than the speed of light. There's what Einstein described as a spooky correlation, but there's no spooky action at a distance. The geometrical picture is the same here. The left observer could try to send a signal to the right observer, but because it can't go at an angle to the vertical more than pi/4, a signal sent by the left observer at best will go at this pi/4 angle, parallel to the horizon, and will end up at the future singularity. So you can enter the wormhole, but you can't go through the wormhole. You'll get stuck at the singularity.
Just a comment.
Yes?
That this extension Isn't it true that just recently I understood that it is not the unique possible maximal extension to the interior of the black hole?
No.
So
it's the unique maximal analytic continuation of the exterior.
Well, if you leave this
let's
space
discuss
for-
that separately, if you don't mind. Now, the part of the space-time that a right observer can see and influence is shown in red. So I imagine the right observer here. Well, the right observer can receive signals. This diagonal line is the future horizon of the right observer. You can receive signals from anywhere in the red triangle or the white one. Traveling at less than the speed of light, they can reach the right boundary. You can send signals to this right triangle or that white one. But the region the right observer can both see and influence is this red triangle. And the region the left observer can both see and influence is this left triangle. And those are disjoint. They're causally disjoint. So the left observer can send signals to this blue region or up here. But the right observer can only receive signals from down here. So they can't communicate. It's a geometrical analog of the left and right observer having two different quantum systems that are entangled with each other. That gives a correlation, but it can't be used to communicate information. And the idea of black hole thermodynamics is that this isn't just an analogy, but in some sense it's the same thing. So maybe in one of the later lectures we'll explain that in the natural state of this two-sided universe looks purely thermal to one observer or the other. So, as understood by Hartle-Hawking in Israel in the 70s and reformulated later, in this universe there's a natural pure state called the thermofield double that to an observer in either the left or right looks exactly thermal at the Hawking temperature. I think I will describe that statement in a later lecture. According to Bekenstein and Hawking, the entropy of this density matrix is the horizon area. And for this ideal solution, it does not matter what you mean by the horizon. It could be this horizon, or it could be this one. It doesn't matter where you measure it. You could measure it here, or here, or here, or here, or here. In the ideal Schwarzschild solution, no matter where you cut the horizon, at any given time and for any horizon, the area is always the same. However, suppose two observers, one living on the left and one on the right, decide to disturb this system. They do this by applying unitary operators, since that's all one can do to a quantum system. Here we have a two-sided system, AB, where A and B represent the left and right exterior regions of the space-time, and we have a pure state, the Hartle-Hawking Israel state of the black hole. The combined system has a pure state density matrix, but as we discussed in the first half of the lecture, the left or right observer separately sees a thermal density matrix. Well, first of all, the left and right observer sees a density matrix that's not a pure state, but for this particular Hartle-Hawking Israel state, rho A and rho B are both thermal. The left observer can manipulate the system by applying a unitary operator to the left of the spacetime. The right observer can manipulate the system by applying a unitary operator to the right. What happens to the geometry when the left or right observer applies a unitary transformation? Well, for example, the right observer can create particles that head into the interior. Of course, they might be massive particles, but I've drawn massless particles that head into the interior at the speed of light, meaning at a pi/4 angle from the vertical in this picture. You can hear in the back, right? The problem is time symmetric, so the right observer can also create a state that had particles in the past that were exiting at the speed of light. When I say the right observer can throw in particles, these particles could just as well be macroscopic objects like tables and chairs. Throwing in tables and chairs increases the black hole mass and therefore the horizon area. So it increases the Bekenstein-Hawking area, which is the thermal entropy, A horizon over 4G. The way it shows up in the picture is that when you have these blue particles coming in and out, the black line I drew before is no longer the horizon seen by this observer. They will still represent, in this particular picture, they will still be the horizon for this observer because we won't change the geometry in that region. But these blue particles will change the geometry in the left of the picture. And therefore, these black diagonal lines, although they still exist in the space-time, they're not the horizon anymore. I haven't tried to draw the picture more realistically to show what the new horizon is. But the horizon, as seen by the right observer, will be to the right of these lines. The left observer can also manipulate the state. So the left observer is throwing in particles, here depicted as diagonal red lines coming into and out, going into the future and coming in from the past. All these manipulations change the state. They change the state by a unitary operator. The left observer can make a unitary operator UA acting on the left part of the state. The right observer can act with unitary operator UB on the right part of the state. And by acting on psi AB with a product unitary, UA tensor UB, you can change the state a lot. But it's not true that you can change everything. What can't you change? Well, there's a limit to what you can change. Unitary evolution will only change the left or right density matrices by conjugation. So it won't change the von Neumann or entanglement entropy. The entropy, the von Neumann entropy of the two density matrices doesn't change. And more generally, the eigenvalues of the density matrices don't change. So in ordinary quantum mechanics, what can't be changed by the two observers separately is precisely the eigenvalues of the density matrices. They can change everything else. If von Neumann entropy can be represented by something in geometry, it'll be represented by something that observers on the two sides cannot change. There's only one place in the space-time that the observers cannot manipulate. It's what's traditionally called the bifurcation surface. That's where, in the original Schwarzschild solution, that was the surface where the two horizons crossed. In this new space-time with all those particles, neither black line is a horizon anymore, and the geometry changes everywhere except at that intersection. So after the two observers have done their worst, the geometry is completely different from what it was before, except in this bifurcation surface. The observers on left and right can do nothing to change the geometry of the surface, but they can do everything else. They can make all kinds of manipulations on its left and right. Now the picture became rather busy. So let's go back to where we started. This was the original picture, and what's called the bifurcation surface is where the two horizons meet. And for Bekenstein-Hawking entropy of the original spacetime, or the original thermal state, the area of that surface or any other surface labeled by any other point on either horizon would be equally good representation of the Bekenstein-Hawking entropy. But when the two observers start changing the space-time, what they don't change is the bifurcation surface. So it's natural that the von Neumann entropy should be the area of the surface, if it's any kind of area. In a formula for the von Neumann entropy, we shouldn't refer to the bifurcation surface as the horizon, because once the space-time is perturbed on the left and right, this surface isn't a horizon anymore. It's still there as a surface in the space-time, but it's not a horizon. What it is, though, is that it's an extremal surface. It's a surface whose area is stationary among all nearby surfaces. In the original space-time, well, you could, for example, use the explicit Schwarzschild metric to show that the area of this surface is stationary, meaning if you move in any direction, you don't change the area. It's actually sufficient to check that from moving this way and also moving this way. And very general properties of general relativity show that the area is actually constant in either direction. So the bifurcation surface, so that would not be true of this point. The area of this surface this is not a stationary area. Remember, every point in the Penrose diagram represents a surface in space-time because the angular coordinates have been suppressed. So each point in that picture really represents a two-sphere with variable area, variable radius and area. The two-sphere corresponding to this point isn't stationary. If you move orthogonally, the derivative of its area is not zero. But the derivative of its area along the horizon is zero. At the bifurcation surface, either direction is along one horizon or the other. So the derivative of the area vanishes. And the bifurcation surface is the only surface in the original space-time where that was true. So a way to describe the bifurcation surface in the original space-time is that it is a two-dimensional surface of stationary area among all nearby surfaces. Now, when we perturb the space-time, the bifurcation surface is no longer on the horizon. It's not on either horizon anymore, but it still is a surface of stationary area. It's called an extremal surface, meaning a surface whose area is stationary among all nearby surfaces. And as I stressed, it remains extremal in the more general space-time that left and right observers can create by their manipulations. This follows from the Einstein equations. So the idea of Ryu and Takanagi, I should say their original work was in a different type of example. But extrapolating their idea to the type of example I'm describing, the idea of Ryu and Takanagi is that the von Neumann entropy of the left or right observers is the area of an extremal surface that separates the two observers. So in the space-time between the two observers, you find an extremal surface, and the area of the extremal surface over 4G is supposed to be the entanglement entropy, the von Neumann entropy of the density matrix of either of the two observers. As I explained, when a whole system is in a pure state, the two subsystems have equal entanglement entropy. I think I explained it. I'm forgetting, sorry. Okay, I did explain it, hopefully. Sorry, I either explained it or I'm about to explain it. I'm forgetting where in the talk I put it. Sorry. Sorry for my confusion. I reorganized the talk a little bit last night, and now I'm forgetting what I did. Anyway, the idea is that, as I either explained or will explain, the entanglement entropy is the same for both observers. And so Ryu and Takanagi give one answer, the area of the extremal surface that separates them. That's to be compared with the thermodynamic entropy, which is given by the horizon area over 4G. Now, the two observers would not measure the same thermodynamic entropy. Maybe one observer threw in a few elementary particles, the other observer threw in tables and chairs. Then the black hole mass on one side is different from what it is on the other side. And since the thermodynamic entropy is determined by the black hole mass, the two observers will actually measure different thermodynamic entropies. They'll have different horizons. I haven't tried to draw the horizons realistically, but one horizon is somewhere here, one is somewhere here. The bifurcation surface is in the no man's land between the two horizons. So In this general situation, there's one von Neumann entropy that the two observers share, and they each have their own private thermal entropy associated to their own horizons. I use the squiggly line instead of an equal sign because both formulas have quantum corrections. Now, you can use Einstein's equations to prove that the extremal surface is always behind the horizon, consistent with the expectation that the von Neumann entropy should be no bigger than the thermal entropy. There's a subtlety, however. There might be multiple extremal surfaces between the left and right boundaries of the figure. There's one we know about. The one that started its life as the bifurcation surface. No matter what these observers do, it will remain as an extremal surface. But when they throw in all these tables and chairs and modify the geometry on the two sides, they might create more extremal surfaces. So the extremal surface that separates between the two observers might not be unique. And the general statement is that the von Neumann entropy is the area of an extremal surface of minimal area that separates the left and the right. In other words, if there are multiple extremal surfaces, then among those extremal surfaces, you pick the one of least area. By the way, it's important that the minimization is only among extremal area surfaces. If you allowed arbitrary variations of a surface, you would never have minimal area, because taking any space-like surface and wiggling it in a time-like direction, you could always reduce its area. So what you do is consider extremal surfaces only, and then you take the minimal area among extremal surfaces. And that is believed to be the von Neumann entropy of the density matrix. Now, once you realize that you have to talk about minimal area among extremal surfaces, it becomes clear that there might be a phase transition in the location of the Ryutakyanagi surface. As you vary some parameters, if there are several extremal surfaces, their areas could change, and there could be a first-order phase transition where what is minimal stops being minimal. As a black hole evaporates, there might be a phase transition in the location of the minimal surface that represents the von Neumann entropy. Just such a phase transition in the field of an evaporating black hole was found 5 years ago by these authors and resolved some of the paradoxes that arise in trying to reconcile the thermal nature of the Hawking process with quantum mechanical unitarity. I want to give at least some idea of why a phase transition was needed. Remember that in the real world, a black hole forms in a state of very low entropy. Let's idealize the situation by imagining the black hole forms in a state of zero entropy. But it wouldn't matter very much if we started in a state of very small entropy instead of zero. So zero entropy would mean the black hole state's in a quantum mechanical pure state. Then we let the black hole evaporate for a long time t. It emits radiation that's very nearly thermal, according to Hawking. By the way, if you wonder why I want to start it in a pure state, it's true that starting the black hole in a low entropy state would not change much in what I want to say, but to prove that, we would need to talk about certain entropy inequalities that I haven't introduced today. So to avoid the need for that, I will idealize the situation by imagining the black hole starts in a pure state. Then we let the black hole evaporate for a long time t. It emits radiation that's very nearly thermal, according to Hawking. So the entropy of the radiation grows roughly in proportion to t. At time t, the black hole is no longer in a pure state. But if quantum mechanics is correct, then there is a pure state that we'll call psi br of t that describes the joint state of the radiation R and the black hole B. B and R refer to the black hole and the radiation. And quantum mechanics says that the overall state remains pure. So if the black hole started in a pure state, then there's a pure state that describes the joint state of the radiation and the black hole. At this point, either the black hole or the radiation can be described by a mixed state density matrix. The black hole density matrix is gotten by tracing the pure state density matrix of the pair over R, and the radiation density matrix is gotten by tracing the same thing over B. Now, it's a basic fact of quantum mechanics, which I guess I didn't explain before the break, that in such a situation, the von Neumann entropy of rho B and rho R are equal. And more generally, it's true that rho B and rho R have the same eigenvalues. That's because of what's called the Schmidt decomposition. The canonical form of a joint state psi br up to unitary transformations of the two Hilbert spaces is like this. Psi br you could think of as a kind of matrix, one entry being from B and one matrix being from R. And by making unitary transformations on the two sides, you can effectively diagonalize it. Well, diagonalizing it means you write it as a sum of black hole states tensored with radiation states, and you can assume that the black hole states and the radiation states that appear in the formula are orthonormal. That's called the Schmidt decomposition of the state. Then the density matrices are like this or like this. So they have the same eigenvalues lambda I squared and the same von Neumann entropy, minus the sum of lambda squared log lambda squared. Now, in the case of an astrophysical black hole, the evaporation is a very slow process. So the temperature we found was of order 1 over the Schwarzschild radius, where the Schwarzschild radius is 2 gm. That means that in each time interval of order the Schwarzschild radius, the black hole emits of order 1 photons. That's what thermal radiation is. In a time which is 1 over the temperature, from a volume of order 1 over the temperature cubed, you emit an energy of order the temperature. So the luminosity, the energy per unit time emitted by the black hole, is of order 1 over Rs squared, or of this order. So roughly the mass of the black hole changes by m dm dt equals minus 1 over g squared m squared. And the time for its mass to change appreciably is of order m cubed over g squared, which for a solar mass black hole is roughly 10 to the 71 seconds. So way, way more than the age of the universe. Anyway, for this very long time, the von Neumann entropy of the black hole keeps slowly growing, and the von Neumann entropy of the radiations likewise keeps growing. And for a very, very long time, there's no problem with it. Meanwhile, the black hole mass is slowly shrinking, and therefore its thermodynamic entropy, which is the Bekenstein-Hawking entropy, the black hole horizon area over 4G, is slowly decreasing. As Don Page pointed out just over 30 years ago, there's no problem with this until a time called the Page time, which is roughly after 1/2 the lifetime of the black hole, but not exactly, at which a naive extrapolation would violate the fundamental inequality. The von Neumann entropy of the black hole is going up, its thermodynamic entropy is going down, and eventually they meet, because if this remains true, as I've written, the thermodynamic entropy goes to 0 as the black hole evaporates, and the von Neumann entropy keeps going up. At a Page time, they become equal. At the Page time, this description must stop. It can't remain valid in the form I've said. When we reach the Page time, the claim that the radiation is purely thermal and that the black hole entropy is the von Neumann entropy of the radiation. Sorry, this should have been, I should have written there the von Neumann, sorry. the claim that the von Neumann entropy of the radiation, which is the same as the von Neumann entropy of the black hole, the claim that it's steadily increasing has to break down. Well, what happens then? Upon further evaporation of the black hole, with its mass continuing to decrease, I should say we expect the black hole does continue to evaporate, because for a solar mass black hole, at this point it's only lost half its mass, roughly. And it's still huge compared to elementary particle scales, and Hawking's approximations appear to still be valid. So we don't expect the evaporation to stop at the page time. We expect the black hole to continue evaporating. And if that's true, since it's losing mass, its thermodynamic entropy goes down. And since its von Neumann entropy is bounded above by its thermodynamic entropy, the von Neumann entropy must therefore start to go down, whereas it had been going up before. So Page argued on physical grounds that what must happen is that once the page time is reached and the inequality is saturated, it will remain saturated for all times. I think you can motivate Page's reasoning as follows. Remember, the black hole formed in a low entropy state, but it looked thermal from the outside. As I said at the very beginning of the first half of the lecture, it's very, very difficult to distinguish a typical microstate drawn from a microcanonical ensemble from true thermal equilibrium. The microphysics is some detailed quantum state, but the macroscopic properties are the same as in equilibrium. So the black hole apparently was born like that. It was born in a low entropy state, but it emitted as if it was in thermal equilibrium. But at the page time, the black hole actually reaches true microscopic thermal equilibrium. At the page time, its von Neumann entropy becomes equal to its thermodynamic entropy. So it finally has reached true microscopic equilibrium. Now, once you're in microscopic equilibrium, as you continue to radiate adiabatically, one would expect one would remain in equilibrium. True microscopic equilibrium means that the von Neumann entropy equals the thermodynamic entropy, and once it's achieved, it's hard to lose it. So the idea is that we started with a black hole in a low entropy, or perhaps a pure state. If one was capable of measuring its microstate, one would have said that the black hole at the beginning was far from true thermal equilibrium, far from having a strictly thermal density matrix. But when we reach the page time and saturate the inequality, the black hole is actually in true thermal equilibrium with very nearly a thermal density matrix. Once it reaches thermal equilibrium, one would expect this to be maintained as the black hole evaporates adiabatically. Remember that black hole evaporation is incredibly slow in the case of an astrophysical black hole. So you can think of the black hole evolving adiabatically, and adiabatic evolution of a system in true thermal equilibrium would be expected to preserve thermal equilibrium. So Page proposed that the evolution, this should have been S. von Neumann. There are a couple of stray characters there. Page proposed that the evolution of the von Neumann entropy of the black hole follows what later authors have called a Page curve. I've plotted the von Neumann entropy of the black hole against time. It goes up roughly linearly in the time. It's not really linear because the black hole is losing mass and the evaporation rate changes. But within a factor of, over a huge, huge time, it's within a factor of 2 or something of being linear. It goes up more or less linearly for a long time. When true thermal equilibrium is reached, it turns around and starts going back down linearly. So this is, as argued by Page, the time history of the von Neumann entropy of a black hole that's born, as in the real world, in the low entropy state and eventually evaporates. Now, in a sense, this isn't really an exotic claim. It's very hard to imagine how you could initialize a burning lump of coal in a quantum mechanical pure state. because it's very hard to put any kind of macroscopic system in a pure state. It's kind of magic that nature creates black holes in states that are very close to being pure, very low entropy compared to their thermodynamic entropy. It would be hard to do that for a burning lump of coal. But theoretically, if you could initialize a burning lump of coal in something close to a pure state, you would expect that its von Neumann entropy would follow a page-like curve. It would emit radiation that would look thermal, and its entropy would grow due to entanglement with the radiation it's emitted, and it would keep growing until true microscopic thermal equilibrium was reached, and then the entropy would have to start going down. The difference of the black hole from the lump of coal is that although it's hard to see how you could initialize a burning lump of coal in a state of very low entropy compared to its thermodynamic entropy, nature does that in the case of black holes by producing them in low energy states, low entropy states. In the limit that the initial black hole mass is very large, the Page curve is believed to converge to a true phase transition. So for any finite mass black hole, it'll be rounded out at the top. But it's believed that the more is the mass of the black hole, the closer this is to being a sharp turnaround. And the phase transition has been interpreted as a phase transition in the quantum extremal surface that computes the von Neumann entropy. According to these authors, the quantum extremal surface is the empty surface prior to the Page time, and at the Page time, it jumps to a location very near the black hole horizon. So in coming lectures, I'll speak a little more of the basis for this claim, and I'll also describe a little more of what still is not understood. So that's actually as much as I planned for today's lecture. I might have finished a little bit ahead of schedule, I'm not sure. Oh, okay. Okay. Well.
Please wait for the microphone if there are questions. Porfa. I was starting to get worried about to signal you that you had 5 minutes, and then you prevented me from my chairman duty.
Okay.
So my question is about the Page curve. You're suggesting that the entropy of the final state, or better, the final state is again a pure state, the black hole.
If we start with a pure state, then quantum mechanics says we always have a pure state.
Am I right that I should say you are not allowed to observe the black hole in the meantime because any observation would destroy the pureness of the state?
Well, it depends on your point of view about what observations mean. If the overall state of the observing apparatus plus the black hole was pure initially, then the final state of the radiation plus the observing apparatus will be pure. Further comments depend on your point of view about what observations mean in quantum mechanics.
I have a question about the Rui-Takanaji proposal.
Yes.
So if the observer on both sides can modify the geometry,
yes,
and they can make the other extremal surface appear,
yes,
is it possible that this surface becomes minimal, and so they modify the entanglement entropy, even if they shouldn't in theory?
Well, if the theory makes any sense, that will never work. So it's certainly not been demonstrated how it will work, but I'm not sure if the no-go theorems are completely general. But one definitely expects that that will never work, given the laws of nature. A question is exactly how much you have to know. Classically, you expect that if the matter system obeys the null energy condition, which all physically sensible matter systems do, that you won't be able to do that. I'm sure that that's true. I'm not certain how completely it's been proved. What's easy to prove is that the original bifurcation surface is behind the horizon of both observers. That's a different statement from the one we need here, though.
So you can create extremal surface, but you don't expect them to be minimal?
Yes.
Okay.
You don't expect them to be minimal among extremal surfaces.
Thank
you. There is one way in the back.
Hi. So up to this point, we argued the island, in some sense, by proof by contradiction. So if we believe all the general principles, then that must be the case. But dynamically, how do you actually get photons to entangle so that actual again?
I missed a few words, but I'm also not sure I understand what the question is. I think the question might be, how do we explicitly see that the radiation entropy starts going down again?
Yes. So
okay.
The effective.
Yeah. My position is that we don't have a good explicit understanding of that. So if you ask me to summarize in one sentence what hasn't been explained. So I think what has been shown is that in a quantum theory in which the Ryu-Takanagi formula and what's called entanglement wedge reconstruction that I didn't explain are true, there would be no further paradoxes. But I don't think we understand in what kind of quantum theory those statements are true.
Thank you.
If there are no other questions,
Well,
is there someone?
Well, there was one question during the lecture, which I didn't want to answer then, but we can hear now.
That's actually about the great assumption. Anyway, the thing is that if you just think about it, if you just give some chance to signature change for analytical extension of the metric from outside to the inside into the black hole, then you get another solution, another sort of the manifold doesn't remain Lorentzian, definitely.
Doesn't or does?
Does not remain Lorentzian.
Okay.
But interior of it becomes quite Riemannian.
Okay, I'd be happy to hear that maybe later on. But I just want to say that, yeah, okay. What this was the unique real analytic extension of the Schwarzschild metric in the exterior. Well, regardless, this was the geometry that describes a pair of black holes in thermal equilibrium, which is what we wanted to study. Well, I'd be happy to hear about the geometry you have in mind, and maybe it would be interesting to study. But to motivate, what I wanted to do in the second half of the lecture was to explain the page curve and to explain the idea that a phase transition of some kind is needed to account for it. And to motivate the idea of measuring the von Neumann entropy, the microscopic entropy, as the area of an extremal surface. And one or two other things along the way. And for those purposes, the geometry that we studied was the right one. But there might be a different geometry we should study for other purposes. So I'll be happy to hear about the geometry that you want to describe.
If there are no other questions, I have a question.
Yes?
Pretty much here you have, let me say, classical quantum mechanics. So quantum mechanics and general relativity.
Yes.
And you are merging them. And there are some holes, some things which don't match.
Yes.
Will they be described next by some quantum gravity kind of theory, or we still have to work on it?
Well, we definitely still have to work on it.
We definitely have to work on it.
I don't know what kind of theory it is in which the Ryu-Takanagi... If we discuss the Ryu-Takanagi formula, probably I'll say a little bit more about path integral computations of entropies, which give answers consistent with what I've claimed in the lecture.
Mm-hmm.
but whose quantum mechanical interpretation in terms of microstates isn't clear.
Okay.
There's definitely something missing. In answer to a questioner in the back, I tried before to say in one sentence what was missing. What's missing is in what kind of quantum mechanical theory are the Ryutakinagi formula and so on true?
Mm-hmm. Oh, there is.
I see a question here.
Can you go back to the page curve a second? So the phase transition slide, yeah, this one. Yeah, so I guess that you said that you expect the growing behavior at first to be proportional to t because the mass is slowly varying, and so at the same time for the decaying one. At some point you said something about the relation with phase transitions and the smoothness of this curve, and I wondered if you could further on that.
Well, for a black hole of any given mass, this is going to be a smooth curve, and there will be no true phase transition. It's believed, though, that the curve is sharper and sharper the bigger is the mass. You might want to remember that any statement in statistical mechanics is only precise in the limit of infinitely many degrees of freedom. So for a black hole, infinitely many degrees of freedom means the mass goes to infinity. So a claim that there is a sharp phase transition is going to have to be a statement about what happens. Sorry, I'm thirsty. What happens in the limit of large mass? It's only in the limit of large mass that you can truly get a sharp phase transition. As I've emphasized, though, astrophysical black holes are, in a sense, very close to the limit of large mass. The solar mass is 10 to the 38 times the Planck mass. So a solar mass black hole, 10 to the 38 isn't infinity, but it's enough to make this a very sharp, very good approximation to a true phase transition.
Thank you.
Okay, I don't see any further question. There is the screen, so unless, Giovanni.
This is just a curiosity. You start a black hole with entropy 0, then you radiate, and then you can have a mixture of states. And then you can have two states that you suppose which are orthogonal. These two states from radiation and from the black hole. Now, what happens if they are not orthogonal? That you can have some transitions between that.
Well,
maybe just a curiosity because, okay.
All you can say in general is that after some time, the black hole and the radiation will be in some pure state, psi br. In general, all it is some state in the Hilbert space. But any state in the Hilbert space has what's called a Schmidt decomposition. It's the analog of diagonalizing a matrix. Here, it's not a square matrix. It's a kind of rectangular matrix. B has n states. R has maybe m states. This is an m by n matrix. And we're diagonalizing it under separate unitary transformations acting on HB and HR. But anyway, up to joint unitary transformations, any psi br can be put in this form. There's no assumption involved. It's just the canonical form, the so-called Schmidt decomposition, the canonical form of any what's called bipartite state. A bipartite state is just a state in the tensor product of two Hilbert spaces, here HB and HR. Any such state can be decomposed in this fashion, where we can assume that the chi's and the chi tildes are orthonormal. There's no assumption involved. It's just a fact of linear algebra that any state can be put in that form. It's convenient to do so because then the density matrices are diagonal, and it becomes obvious that the two density matrices have the same entropy, which is what I was trying to prove when I did this calculation. Any other questions?
Okay. So if there are no more questions, we reconvene tomorrow for islands and entropy, or islands? Yes, islands and entropy, or something.
We'll decide.
At 10:30. At 10:30 tomorrow, we'll know. Okay. Let's thank again the speaker. Okay. I don't know. slides.
They will be available in the afternoon.
They will be available in the afternoon, but you can see the whole thing on YouTube. Yeah. Va bene, vai.